All right, at this stage, you should have a really good understanding of how to solve an equation that involves an exponential function like the one you see in the middle of the screen here. And one of the reasons why we learn about logarithms is because they actually help us solve really, really powerful exponential functions, like things that you'll experience in your life. For example, interest rates on credit cards or home loans or car loans, or it's the way that you save money for your retirement so that you have money and you don't have to work when you're at the end of your life. So I just wanted to make sure that you had exposure to some information about how these logarithms are actually helpful for us. So I'll read the example and we'll work through a few of them together, and then I'll give you a few that you can try on your own. So $400 is added to your savings account that pays 4.28% annual interest. The equation that models this is y equals 400 times 1.0428 to the power of t. How much time would it take for the account to reach $520? So first things first is we really need to understand what these variables mean, and t typically represents time, and that's what annual means. Annual means every year, and the y value means the amount of money that's in your account. So if I were to put 1 as your time measurement, if I were to change t to be 1, and I put this into a calculator, that would be how much money was added after 1 year. And if we really want to check ourselves, we can check that we're doing it right, because if we put 0, meaning 0 time has gone by, we would get $400. And that's exactly what we want, because we start with $400. But we're not doing that. We are thinking about what's happening when we have an output of $520. So instead of the y value being the output for a specific time, we're going to substitute the y value with 520. And so really we're going to see 520 equal that 400 times the 1.0428 to the power of t. And now this is an exponential function that is very easily solvable. We'll want to divide by 400 on both sides. So 520 divided by 400 is 1.3 equals 1.0428 to the power of t. And then I'm going to use my knowledge of how to solve by converting it into a logarithm. So log base, and the base is a big long number now, 1.0428 of my answer, 1.3, equals the amount of time that goes by. And this is in time in terms of years. And so I'm going to put it into a calculator. Log of base 1.0428 of 1.3 is going to be 6.2602. So that means that if the interest rate was what I said it was at the beginning, the interest rate was 4.28%, and we wanted to get $520, but we originally put in $400, it would take about 6 years and a quarter of a year, so through about 3 months. So this is we would say this is the number of years, and we want to add a label to that for 6.26 years it would take to get $520. All right, here's another information. In fact, this is a little bit false because the world doesn't grow exponentially anymore. At one point in time it did, but for example, let's assume that we were at that stage in our history. And this is actually a while ago because we're talking about the year 2000. So the world population grows incredibly fast. In fact, it's exponential, which it's not. It grows approximately 22% each year. In the year 2000, the population was 6.122 billion people. So y equals 1.3 6.122 times 1.22 to the power of t. What year will the population be 8 billion people? So here we go. There's that, and then we're going to answer a second question. When was the population 1 billion people? Time, we're talking about the number of years, and we're talking about the number of people in terms of billions. So if we're using 6.122 here, our number is just going to be 8 when we plug it in for B. So we've got 8 equals 6.122 times 1.22 to the power of t. And notice, I don't know if you know this, but the 22% is what's creating that 1.22. This just happens to be the same number, which is kind of funny, actually. But we have to divide by 6.122 first. So we got 1.3067 and some change equals 1.22 to the power of t. Then I got to log it. So I got log of base 1.22 of 1.3067. And in a calculator, I would use the answer button so that I got the correct answer next time. And we get 1.3454 equals t, which means the years. So to grow from 6 billion people to 8 billion people, it takes about a year, a little bit less than a year, which is really fast, actually. This idea is going to still work the same way, except we're going to put in 1 billion people. So we're going to do kind of the same problem, but just with 1 billion people. So 1 equals 6.122 times 1.22 to the power of t, divided by 6.122, and we get 0.61633 and some change equals 1.22 to the power of t. And in a calculator, t is going to equal, sorry, I should have done the log. I need to do the log. Log base 1.22 of 0.1633 equals t, and t is going to equal negative 9.112, let's call it. Well, that doesn't make sense. That means that only 9 years ago, in 1991, was it a billion people, which is not true. So this is not, this is 9 years ago. 9 years ago, so that would be 2000 minus 9.112, so 1991 and some change. The year 1991 was when this model would predict that there would be 1 billion people, which is definitely not true. So we're not going to take that as at its word. But just know that the world doesn't grow this way, and this is a poor model for this situation. All right, so we're going to I'm going to let you try this on your own. Please do stop the video. I will reveal the answer in just a few moments. But we're looking at a temperature. Some things to know is that T almost always means time in this model. And I'll even be a little bit more specific and say time is the number of minutes. Time is minutes since midnight. Okay. So pause the video and give it a try. All right, hopefully you've given it a try by now. We know that T is minutes and the temperature is the Y value. So 130 equals 170 times 0.98 to the power of T. Divide by 170. So we get 0.98 to the power of T equals 13 over 17, or 130 over 70, and log base 0.98 of 130 over 170, and I keep it as a fraction to make it more accurate. Otherwise, we'll lose some correctness. It's called catastrophic cancellation. It's when you accidentally get rid of some decimals, then you actually lose a lot of accuracy. And it looks like 13.27 equals t, and that's the number of minutes. Minutes since midnight. Minutes after midnight. Because t represents the minutes since midnight, and so 13 minutes after midnight, the coffee will have cooled a little bit. Hopefully we're thinking about coffee. Right, in our last one, there's an exponential function. This might be for someone's house. Someone could have bought a house and they have a 5% interest loan. How much is it going to cost exactly? $2,000. And maybe we're thinking about t in terms of years since the purchase of the house, potentially, or since the last time they added money to it or bought it or whatnot. Give it a try and solve and interpret the results to a solution of an exponential function like this. All right. What does this 3.2704 mean? It means the years until price is $200,000. All right. Keep practicing. Good luck. This is really just an exercise of substituting the value you're interested in into the y value, and then using logarithms to solve for the unknown. Thanks for watching.